convergent sequences are unique. A sequence can only converge to one and only one limit. Theorem 1.2 said that every convergent sequence was bounded. Now, we won't be seeing a proof of Theorem 1.3, the monotone convergence theorem, but we will be using it. The monotone convergence theorem is quite a useful theorem in real analysis when you're analyzing the behavior of sequences and series, when we come to look at series. And it says that if you know your sequence is an increasing one or a decreasing one, okay, so if it's not bouncing around all over the place, if it is got some consistent behavior of either increasing or decreasing, and if you also know that it's bounded, okay, so it isn't just zooming off to infinity, you know, getting larger and larger without any upper bound. If you know it's increasing and there's an upper bound, the monotone convergence theorem tells us that the sequence has to be convergent. And just that fact, knowing that a limit exists for the sequence, is often an important step in being able to find the limit as well. And it applies equally well to decreasing sequences that are bounded below. You've got a decreasing sequence of numbers which never goes below some lower threshold, then that sequence of numbers has to be convergent and has to have a real limit. Now, the proof of that is not within the scope of this course, but the way you should think about it is it's really part of the definition of the real numbers, that the real numbers have this property. So today what we're going to look at is the algebra of limits theorem. This is one of the kind of the main results in this section. And as I introduced it yesterday, so I won't do a huge long introduction into it now, but this is a theorem that allows us to draw conclusions about the convergence of complicated series based on knowledge of the convergence of the bits and pieces that are put together to form the complicated sequence. It comes in three forms. It comes in a linear form, a product form, and a quotient form. So we'll just have a look at the statement, and we'll first off look at a couple of examples, and then we'll think about going through the proof of it. So the situation that we're going to apply it in is we're going to suppose we've got two convergent sequences already. So I've got a sequence of elements AN and a sequence of elements BN, and the A's converge to A, the B's converge to B. Okay? So I've got two sequences that have a limit. The linearity part, the linear combinations part, says, well, if I form a new third sequence, and if the terms of this new third sequence are always the same linear combination of the appropriate terms from my sequences A and B, so my new sequence has a term alpha AN plus beta BN, the alpha and beta are just two fixed coefficients, then the theorem tells me this new sequence that I formed here, okay, which is made up out of AN and BN in a linear way, multiplying them by coefficients and adding the results, it tells me that this new sequence is also convergent. Okay? So the convergence of AN and BN causes this new sequence to be convergent as well. And the limit that it has is very nice. Okay? The limit that it has is the same linear combination of the limits, the same coefficients alpha and beta working on the limits that were used in the construction of the sequence. The other two parts are similar, but they apply to different operations. Not the operation of addition of the two parts, but for instance, in the product form, we're talking about the multiplication. Okay? So if I form a new sequence, which has the form, its first term is A1, B1, A1 multiplied by B1. Its second term is A2 multiplied by B2, etc. So the nth term of my new sequence is AN multiplied by BN. The theorem tells us that this new sequence is also convergent. And what limit could it have except for A times B? Okay? So you form a new sequence by multiplying together corresponding terms of your two sequences, and the limit that this new sequence has is indeed the product of the two limits. And then very similar result, except this time talking about quotients. And when you're talking about quotients, putting things below the line, you have to avoid 0, okay? Because it isn't defined to divide something by 0. So in order to make sense of these fractions an over bn, we have to know that bn is never 0. And to make sense of the limit a over b, we have to make sure that b is not 0. Okay. Now, before we get into the proof of these, let's look at a worked example of using the theorem. Okay. So here is one instance where we can use the algebra of limits theorem. We'll look at this example and also look at one of the exercises in the questions at the back of this chapter. So in this example here, example 1.8, we're presented with a sequence xn on the top, and it's a fairly complicated sequence. The formula for it is relatively complicated. I'll put this on the two screens while we're on it. But we can spot that the ingredients used in the definition of the sequence are familiar. We've got powers of n. Okay. So we would like to use the algebra of limits theorem to draw conclusions about the limit of this new sequence xn. Now, one might be tempted to straight away apply the quotient form of the algebra of limits theorem, okay, because the main operation here is the division of those two polynomials. So you could say the limit of xn is the limit of the top part divided by the limit of the bottom part. But that would not be correct, because the top part, the 2n squared minus n, that is not a convergent sequence. Okay? That quantity is getting larger and larger without any upper bound. As is the denominator, minus 3n squared plus 2, that's getting larger and larger without any upper bound as well. So we can't apply the quotient form of the algebra of limits theorem yet, because we don't have a quotient of convergent sequences. But if we rearrange the term defining xn a little bit, then we can. Okay? And the way that's done is to divide the fraction 2n squared minus n over minus 3n squared plus 2, to divide the top and bottom there by n squared. So that's what's done to get to this step down here. So instead, we've got 2 minus 1 over n on the top and minus 3 plus 2 over n squared on the bottom. And we've also applied part of the linearity form of the algebra of limits theorem, because what we were looking at the limit of 2/3 times something, and now I'm just saying that that's 2/3 times the limit of the sequence. Okay. Now, the benefit of dividing above and below by n squared is because it changes the numerator and the denominator in such a way that the numerator, 2 minus 1 over n, is now a convergent sequence. 2 minus 1 over n is convergent to 2. And the denominator part, minus 3 plus 2 over n squared, that's now a convergent sequence. And that's converging to the limit minus 3. 2 over n squared part is converging to 0. So now we are justified in applying the quotient rule and saying that the limit of this big fraction is the limit of the top part divided by the limit of the bottom part. So we're applying the quotient form of the algebra of limits theorem there. And then we have to apply the linearity form again to say that the limit of the constant 2 minus 1 over n, that's going to be the limit of the constant 2. The limit of a constant is just that same constant, minus the limit of 1 over n, that's 0. So you get the limit of the top part is 2. And similarly, the limit of the bottom part comes out to be minus 3, because the 2 over n squared part we know converges to 0. We've still got the 2/3 at front. So overall, we have the limit minus 4 over 9. Okay. So you can see in a number of locations there, using the various parts of the algebra of limits theorem to draw conclusions about the limit of that sequence. We can find a second example if we look in the exercises here. If we scroll forward through to exercise 10. So exercise 10 concerns a sequence that's defined by a recurrence relation. Now, there's a bit of context given for it there. It's a sequence that occurs from applying something called Newton's method to finding a root, or 0, of that polynomial x squared minus 2. Now, Newton's method is a numerical algorithm for finding roots of an equation. You will learn about it in your second year, in the numerical methods unit in your second year. It's one of the first kind of numerical approximation algorithms that one learns about. But that's just giving a bit of context to say where this kind of recurrence relation might arise in practice. So the recurrence relation is defined by, well, it's got an initial term C1, which is 1, and then after that, the terms are defined as 2/3 times the previous term plus 2 divided by 3 times the previous term squared. Okay, and then the question comes, well, what's the value of the limit of this equation? Now, when you're setting up Newton's method and describing Newton's method, you find out that the sequence it produces should converge to a root of the equation. You can kind of guess what the root is to begin with. I mean, what is the root of x cubed minus 2 equals 0? Well, of course, that implies that x is the cubed root of 2. That's the solution. So that's the limit that we're expecting to get from this equation. And the way the argument goes, which is based on the algebra of limits theorem, is if we assume that the limit does exist, so if we assume that the limit as n goes to infinity of Cn is equal to C, okay? If we assume that the limit exists, then we can apply, and moreover, there's a few extra conditions here. We'll assume it's a non-zero limit. Then we can apply the algebra of limits theorem, this theorem which we're about to prove, apply the algebra of limits theorem to the recurrence relation itself, okay, the recurrence relation being this equation here, relating Cn plus 1 to Cn, you take the limit of both sides. Now the limit of the left-hand side, well, what is Cn plus 1 converging to? Well, that's converging to this quantity C. Okay? C is the limit of the sequence Cn. So the term Cn plus 1 will be converging to C as well. So they're just one step ahead of Cn. And this will be equal to the limit of the right-hand side. This is a C, it's like a scripty handwriting C, yeah? Letter C, is that okay? So this should be equal to the limit of the right-hand side. Okay, and then we break down the, so that's got the C here, we break down the right-hand side by just applying the algebra of limits theorem. So what is the limit of this plus this? Well, it's the limit of the first bit, which will be 2/3 times C, plus the limit of the second bit, which will be 2/3 times C squared. So by applying the algebra of limits theorem to the recurrence relation itself, we get an equation which is satisfied by the limit. And to clear the denominators here, you multiply both sides by C squared to get C cubed is equal to 2/3 of C cubed plus 2/3. Is that right? And bring the C cubes over the other side. That tells you that 1/3 C cubed is equal to 2/3. And the 3's cancel, so that implies that C is the cube root of 2. Which was the answer we were expecting. It was a pretty simple polynomial to begin with, so we knew that we were expecting the root cube root of 2. Yes? Oh, yes, I didn't put in, but the infinity? Is that what you were saying? Yeah, sorry, thank you. Write that down. So that shows again the application of the algebra of limits theorem, because the breakup of this bracket here, this whole term, to here, that's justified by the algebra of limits theorem. It allows us to take a limit of this complicated sequence, which is built up out of the simpler sequence Cn, and it allows us to substitute the limit of Cn into that arithmetic expression, 2/3 times Cn plus 2 over 3 times Cn squared to get this equation just involving the limit C. Then that can be solved algebraically to find the value of the limit. Okay. So what we'd like to do now is to do the proof of this theorem. So there's a few different parts. I'm going to prove the linearity part and the product part, and then I'm going to leave the quotient part with you to prove, and then I've got a handout here which kind of gives you guidance on how to prove it. It's kind of a staged exercise to take you through your own construction of the proof of that. And this is something we can discuss in the tutorials, probably not this week because I've only just given it to you, but next week's tutorial. Okay, are people finished with this sheet? Yeah. Okay. So we're coming back now to Theorem 1.4. Okay. Okay, so we're going to prove this now. So we need to be very clear on where we're starting from. Okay, the assumptions that we make to give us the results that we're going to be using. Okay, so we assume that AN and BN are convergent. Convergent sequences, strictly speaking, should be curly brackets around those, and that AN converges to A, so this is just the information given in the statement, and that BN converges to B. Those are the assumptions we're making. We're allowed to use those facts in our proof. We need to prove that alpha AN plus beta BN converges to alpha A plus beta B. Okay, so I'm just making a declaration at the start, making it clear to myself what I'm doing. So in order to prove this convergence, we have to show that the definition of convergence is satisfied for this statement. Okay, this is what we're trying to prove here in the green box. So we have to demonstrate that the definition of convergence holds for this. What that means is, if somebody gives us a positive number epsilon, remember the positive number epsilon is the size, the radius of this interval around the limit, we have to prove that there is some point after which all of these terms, alpha AN plus beta BN, there's some point after which all of those terms live completely inside that interval of size, of radius epsilon around the limit. Okay? And we have to be able to do that no matter what positive value of epsilon is given to us. Okay? So we will need to show that there exists an n such that if n is greater than or equal to n, the absolute value of alpha AN plus beta BN minus the limit, which is alpha A plus beta B, we have to show that this is less than epsilon.
What's up after that?
We, such that if, sorry, IF, yeah. Oh, it should be. I should be trying to capture this. Just pop this up here. Okay, so how are we going to do it? How are we going to find the point after which this inequality is true? At the moment, what's inside the modulus here, it's all the a's and b's mixed up. So we can re-express this absolute value first. So I want to rewrite this absolute value in a sensible way. What I want to do is I want to gather all the a stuff together and gather all the b stuff together. Okay, so that's just multiplying the minus sign into the bracket, bringing all the a stuff together, bringing all the b stuff together, and factorizing out the alpha, beta. Okay. And we're trying to show that this inequality here is strictly less than epsilon. So in other words, we're trying to control the size of this absolute value. We're trying to make this absolute value be smaller than epsilon. We're trying to make this absolute value smaller. So we will use a basic fact about absolute value. This is for all numbers x, y, the absolute value of x plus y is always less than or equal to the absolute value of x plus the absolute value of y. Okay, this is called the triangle inequality. It's fairly easy to understand for just real numbers, and it's just to do with dealing with the different cases of whether x and y might be positive or negative, and so on. But it's actually an example of quite a deep mathematical fact, which comes up a lot in vector spaces and analysis. So you'll come across this further on in your studies as well. But it gives you a way to break down an absolute value in terms of the absolute value of the different parts. Okay? And you get something bigger. You see, I'm trying to make this absolute value small. And you can see that it's made up out of basically the difference between an and its limit and bn and its limit. But we know both of those sequences are convergent. It says so at the top of the page, assuming that they're convergent. So this difference here does get small because an is convergent to a. So this difference here will be getting very small, as will this difference here, bn minus b, because bn is convergent. So that's getting very small as well. I just have to use the fact that they're both getting small to argue carefully then that I can make the whole thing small. So if I apply this triangle inequality to the absolute value that I'm looking at, I can say that it's less than or equal to the absolute value of alpha, and I don't know whether alpha is positive or negative, so I take its absolute value there, plus the absolute value of beta times the absolute value of bn minus b. So that's applying the triangle inequality. I'm splitting this up using the triangle inequality. So now I'm trying to control the size of this absolute value on the left. So if I can control the size of this combination on the right, if I can make the combination on the right less than epsilon, then I'll know that the absolute value on the left has to be less than epsilon. Okay? Because it is no bigger than this combination on the right. And I can control the size of these two quantities here, an minus a, bn minus b. I can make those as small as I want because an is convergent to a, bn is convergent to b. So by convergence of an and Bn, there exists 2 points, n1 and an n2, and these 2 points satisfy these two conditions if n is bigger than or equal to n1, the absolute value of an minus a. Now I can choose this to be as small as I want. And I just have to choose it to be small enough, and for the bn minus b as well, so that when I add them all together, I get something less than epsilon. So I'm going to choose it less than epsilon over 2 times the absolute value of alpha. And similarly, for n2 is chosen so that the absolute value of bn minus b is strictly less than the corresponding thing, epsilon over 2 times the absolute value of beta. Now I'm allowed to do that because an is convergent to n. So this absolute value is getting arbitrarily as is. And you can see why I've chosen them to be those values, because when I substitute in these upper bounds to this expression up here, the alphas will cancel. I'll have epsilon over 2 plus, then the betas will cancel, and I'll have epsilon over 2. So a half of epsilon plus a half of epsilon. So in other words, I'll have epsilon on the right-hand side. And these are strict upper bounds. So this whole thing here on the left will be strictly less than epsilon. Then choosing, and remember the overall aim is we have to show that there exists an n. Well, here comes what the n is. The n is chosen to be the maximum of these two, n1 and n2. So then if n is strictly greater than this maximum, capital N, the inequality I'm interested in, alpha an minus a, plus beta times bn minus b, the absolute value of all this can be made strictly less than. So here I make the substitutions. I substitute in these strict upper bounds for these two quantities on the right. And that's those smaller radii were carefully chosen so that when you combine them in that way, they come out as exactly epsilon. This shows the power of this formal definition of convergence. We're able to prove this quite general result. If you take any two old convergence sequences, an a and a bn, combine them together in this way, an alpha times an plus a beta times bn, we again get a convergence sequence. And its limit is exactly alpha times a plus beta times b. I better just conclude that proof. So this shows the definition of convergence is such. Because remember, we declared at the top that we will need to show that there exists an n with this property. But where is the n? The n was chosen here. Here is the existence of the capital N. It's chosen to be the maximum of these two numbers. But we will need to show that there exists an n. So that's where we declared what we had to do. Here we did it. So we've satisfied the definition of convergence. Any questions about the way I've laid out that argument, that proof? Now it does repay further study again. Okay, you should study this until, and for the benefit of the recording maybe, and the benefit of the other exercises, until you can understand how the definition of convergence is working. Okay? How it's being exploited, because we assumed we had two convergent sequences, so I was allowed to use the definition of convergence, and I used it here, where I was able to say that there exist these 2 points, capital N1 and capital N2, that can make these absolute values small. And then by using the N1 and N2, I was able to show that the definition of convergence is satisfied for this new sequence, alpha an plus b to the 1. Okay, let's do a similar thing for the product rule. Can I remove that sheet now? Everybody got it? So the product rule. Now the same assumptions are at play. We're assuming AN is converging to A and BN is converging to B. Product form. Okay, now what's the task? Again, we let epsilon greater than 0 be given. So anybody can give us any positive epsilon number. And we have to show that this feels a little bit repetitious. We're just repeating the definition each time, but it is good practice like this when you're doing these proofs for the first time to just repeat everything to yourself, make it very clear what the task is at each point. So we have to show that there exists a point capital N which satisfies if n is bigger than capital N, then the absolute value of an times bn minus ab is strictly less than that. Now, we're going to approach this in a strategic way. So first, we prove a special case. And also what we're going to do is we're going to show you the way we can reuse results we've already proved to prove more. So I'm going to prove a special case of this. So I want to examine a very simple type of situation. So not completely general. We'll prove a special case where both of the limits a and b happen to be 0. So I'm throwing in an extra assumption here. I'm assuming that the two sequences I'm dealing with are both converging to 0. So this inequality becomes the inequality I have to show is eventually satisfied becomes the absolute value of an, bn, strictly less than epsilon. I'll be looking at an, bn minus 0, so I'm just looking at the absolute value of a and b. And this makes life a lot easier. Notice that the absolute value of a and bn is equal to the absolute value of an times the absolute value of b. Now, both of these sequences are converging to 0. So I'm free to make them as small as possible. I'm free to wait around, and eventually I'll observe absolute value of an getting arbitrarily small, observe absolute value of bn getting arbitrarily small. So what degree of smallness should I wait around to observe in an? And what degree of smallness should I wait for it to occur in bn? I want to wait until I see the situation such that when you multiply them together, you get something less than epsilon. So there exists two numbers, n1 and n2, such that if n is bigger than n1, the absolute value of an will be less than, and I can choose any positive number that goes here. And if n is bigger than n2, the absolute value of bn, and no matter what positive number I write down here, I can write down any positive numbers here, because I know they're convergent. So I know their absolute value get arbitrarily small. So what's the correct choice? How small should I wait for these things to get? Any suggestions? I want to see them get small enough so that when you multiply them together, you get something smaller than epsilon. Well, before we waited around until they more or less got smaller than half of epsilon. So that when you added them together, you got something smaller than epsilon. Root epsilon. Yeah. We're just kind of mirroring the operation that's at work here. Epsilon is a positive number, so the square root of epsilon will be a positive number. And I know they're converging to 0. So if you wait around long enough until points n1 and n2, you will eventually see them get smaller than root epsilon. So then it finishes off in the same way as before. We let n be the maximum of n1 and n2. So now, if my n is bigger than capital N, then I know that both these conditions here, n bigger than n1 and n bigger than n2, those are both satisfied, because n was chosen to be the larger of the two. So this absolute value, which is equal to the product of the absolute values, this is strictly less than root epsilon times root epsilon, which is epsilon. So the task I gave myself at the top, we have to show there exists an n. That's what I have to demonstrate to prove convergence. Find this n that makes this absolute value less than epsilon. Well, in the special case of zero limits, the n that makes it work is this n here, the maximum of n1 and n2. That n does exist because the n1 and n2 exist. So one of them is larger, and that's the correct value to choose. So this proves convergence in this special case. Okay, I haven't proved the product rule in general. I've only proved it for sequences that are converging to 0. Well, now to complete the proof, I don't have to give another argument based on epsilons and n's. Instead, I can combine this special case, and the reason we prove special cases in this kind of way is to make the general case more easier. I combine this special case with the linearity form we proved 10 minutes ago. So to complete the product form, combine this special case with the linearity part from before. So if AN converges to A, and BN converges to B, so I'm not insisting that the A and B are 0 now, but this implies that this compound sequence, AN minus A converges to 0, BN minus B converges to 0. If I subtract those constants A and B from the sequence AN and BN, I get something that's converging to 0. So that implies that the limit as n goes to infinity of the product of these two is equal to 0. Okay, that's by the special case. So I've got two sequences converging to 0. I multiply them together. That is a new sequence which has a limit of 0. But now when I multiply out this bracket, I get 4 terms, AN BN minus ABN minus BAN plus AB. Okay, that's just multiplying out the brackets. Now after multiplying out the brackets, I can apply the linearity. Because here I just have a collection of things added and multiplied together. And some of the things are multiplied by these fixed coefficients, a and b. So the limit of an and bn, that's what I'm interested in, minus a times the limit of bn minus b times the limit of an plus, well, plus the limit of ab, but ab is just a constant. So its limit is ab, that's equal to 0. But that implies this thing I'm interested in, the limit of an times bn, well, I know what the limit of bn is. It's just b. I know what the limit of an is, that's just a. And this is still plus ab here. Well, you see these two cancel. Got minus ab plus ab. That cancels. And I've got 1 minus ab left. I can now shoot that across to the other side. So that implies that the limit, as n goes to infinity, of an bn is equal to 8. So I cancel these two and bring that over the other side. So then suddenly I've got the general form of the product. My an converges to a, my bn converges to b at the top. Now I've got the conclusion that the limit of an times bn is a times b. Yes?
I don't know if this is simple. Why is it not that it's BA? Surely the minus AB and positive AB.
Well, yeah, BA, AB. Two numbers multiplied together. So you're correct, but I'm also, so we're both correct.
Yeah.
Yeah. Okay. So there only remains to prove the quotient case. Now the quotient case can be proved in a similar way, and I've got a guided construction here, a sheet which talks you through the various steps. So I'm going to leave this with you during the week, and we can discuss it next week. I'll release the solution. Okay, just don't go crazy yet. Any more queries? Any more questions or clarifications? Okay, please, still a question there. We haven't finished yet. Yeah.
The last part of it. I didn't get to the last answer.
From the second last line to the last line. Okay, just please take it easy. So going from, so like from this third last line to here, I was substituting in the definition of the limit. So the limit of bn is b, the limit of an is a. And then I was just noticing, you know, this is the thing we're interested in. And then we got these three numbers. But they're all the same. I've got minus, minus, plus. So two of them just cancel, and then the minus one just moves over the other side of the equation. So you just got AB on the right. Okay, so as you go, yeah, another question here.
How do I check your
By
videos? Your videos.
videos from the Moodle page. You go to the Moodle page, scroll down, there's an embedded YouTube playlist there in the middle. Okay, shh. Again, yes, so the scans of the notes are in YouTube comments below the videos. I'll show you just here. Now on your way out, take one of these handouts. I'll leave two files here, they're both the same. Just take one of these sheets.